What's up, guys? It's Mr. B, and today we're going to go ahead and talk about voltage in series parallel circuits. So previously we talked about voltage in a series circuit, and we found out that all the components in the circuit have to share the applied voltage or the power supply voltage. And then we talked about a parallel circuit where each item in the circuit has their own path to the power supply, and they will all receive the same amount of voltage as the power supply or the applied voltage. Now, what we're going to do is we're going to take a series circuit and a parallel circuit, and we're going to essentially merge those two circuits together, and now we have something called a series parallel circuit. So if you were to take a series circuit and you had two components in it, and then you took another component and you put it in parallel, but only to one of the components in your series circuit, now you've just created something called a series parallel circuit. Because that one that you just put in parallel to a component doesn't have its own path back to the power supply, because it still has to go through the other component that's in series. I'll explain all of this to you in our procedure today, and it'll make a lot more sense when we start covering total resistance in a circuit and Ohm's law. But for now, we just want to know the basic concept of a series parallel circuit. So let's go ahead and get started with our procedure today.
Okay, so now we're going to go ahead and measure voltage in a series parallel circuit. So I'm going to start right here. I have my power supply. I'm going to go ahead and turn my multimeter to DC. I'm going to go measure my power supply just to make sure I have power. And I have 5.9 volts. So now what I'm going to do is I'm going to start with a series circuit, so that way you can see that. And then I'm going to change it into a series parallel. So I'm going to leave my power supply. I'm going to go to a light. I'm going to leave this light. I'm going to go to another light. And then I'm going to come back to the power supply. So as you can see, we have a series circuit. What we learned before is if these had equal resistance, that they would split the voltage applied. Now, if they were different resistance, they would get proportional voltage depending on their resistance. So if we measure this one, I got 3.2, and then we measure this one, I got 2.6. So because they vary in resistance a little bit, they are close, but they're not exact. Now, we said we're going to have a series parallel circuit, so I'm going to make one light in parallel to only a light. So that means that this light bulb right here is going to receive power from here. When we had a parallel circuit, every item had its own path to the power supply. In this scenario, they don't. So you come off the negative power supply, it powers this light and this light. But in order to get to this one, it has to go through these lights right here. So this one doesn't have its own path to the negative side. This one has its own path to the positive though. Now if you look at these two, they want to get back to the positive, they have to go through this light right here. So none of the lights in this scenario have their own paths back to the positive and the negative. So it makes the voltage act a little different in the circuit. Now it's hard to understand because we haven't learned about doing resistance total. So I could sit there and tell you that this one was 15 ohms and this one was 15 ohms. And when you figure out resistance total in parallel circuits, you have to first multiply the first resistor by the second resistor, and then you need to divide that by the first resistor added by the second resistor. And there's a lot of math that goes involved that we will learn later. What you need to know now, though, is that you got to factor this as a unit, and you need to start with the parallel side. So it's going to be a little different than what we've done before, but if I measure the voltage here, the light is on, it may be hard to see, but I have 1.5 volts. And if I measure the light here, I have 1.5 volts. And if you were thinking about this like a series circuit, 1.5, 1.5, they all have to add up to the applied. That's not the case. Because if that was the case, if this was 1.5, 1.5, that would leave about 3 for this. but I'm going to tell you now that this one's going to be receiving more than 3. If you look, this one's receiving 4.5 now. And you tell yourself, well, how can this be more than what the applied voltage is? What you need to do is you need to factor this right here, the portion that's in parallel, as a unit. Now, if you factor that in as a unit and you say this unit right here has 1.5 and you have 6 over here, the rest of that will go to here. So 6 minus 1.5 should equal somewhere around 4.5. And if you notice, we have 4.4. So this is just stealing power essentially from here. It is in parallel to this item right here. But because of the way Ohm's law works and doing your resistance totals, you actually will lose, this unit will lose a resistance total because you put an item in parallel, which means this one will now receive a higher voltage because this one is still considered as a unit at 15 ohms, where now these are considered at a unit of 7.5 and 7.5. So when you're dealing with a series parallel circuit, we will make more sense of it later once we do Ohm's law and resistance total, but for now I want you to start with the parallel side, factor it as one unit, and then determine how much is left for the light in series. Thanks, I hope you enjoyed.